This question comes from Rob, who asks, could you build a jetpack using rifles that fire downward? Surprisingly, the answer is yes. The idea behind it is straightforward. When you fire a bullet forward, the recoil pushes you backwards. That's Newton's third law. So if instead you fire bullets downward, the recoil force should push you upward. But before we get too excited, we need to answer an important question. Can a rapidly firing gun even lift itself? Imagine a rifle that weighs 10 pounds. If it produces only 8 pounds of continuous recoil force while firing, it won't lift off the ground. It can't even support its own weight, let alone carry a person. In aerospace engineering, this comparison between thrust and weight is called the thrust-to-weight ratio. If that ratio is less than 1, meaning thrust is weaker than weight, the vehicle simply cannot take off. For example, the Saturn V rocket had a thrust-to-weight ratio of about 1.5 at launch. Interestingly, many automatic firearms also land somewhere around that same number. That means if you stood one upright and fired it remotely, it would actually rise into the air while shooting. Now let's talk about what determines thrust. The force generated by a rocket or a fast-firing gun depends on two things: how much mass is being expelled and how fast that mass is moving. Multiply those together and you get thrust. Suppose a self-loading rifle weighs 10 pounds. If it fires 10 bullets per second, each weighing 10 grams and traveling at 700 meters per second, the stream of bullets alone produces roughly 15 pounds of thrust. But bullets aren't the only thing coming out of the barrel. There's also high-pressure gas and burning debris. That extra exhaust can increase total thrust by around 30%, depending on the weapon design and ammunition. Another efficiency factor is whether you eject the spent shell casings or keep them on board. For maximum performance, we'll assume they're thrown out. After all, if you're firing bullets at the ground to stay airborne, safety probably isn't your main concern. So what does this mean for our jetpack? One self-loading rifle can lift itself, but it only produces about 5 extra pounds of upward force beyond its own weight. That's barely enough to lift a small animal, definitely not a human. So let's scale up. If one rifle gives 5 extra pounds, 2 rifles give 10, and now you can see the direction this is going. With around 30 rifles firing downward together, you could just barely support a 150-pound person. That setup would allow hovering, but not much climbing. With 40 rifles, you'd start accelerating upward at about 0.1 g. With 60 rifles, maybe 0.2 g. And as you keep adding more rifles, something interesting happens. The passenger's weight gets distributed across so many engines that it becomes less significant. Eventually, the system's thrust-to-weight ratio starts approaching that of a single unloaded rifle. That would mean upward acceleration of roughly half a g, around 5 meters per second squared. But there's a catch: fuel, or in this case, ammunition. Carrying more bullets increases weight. Each bullet weighs about 10 grams, and the cartridge can weigh roughly twice that. If you load too much ammunition, the rifles become too heavy to lift off in the first place. In fact, beyond roughly 150 rounds per rifle, performance drops off because the added mass cancels out the extra firing time. This reveals an optimal configuration: a very large number of rifles, perhaps 300 or more, each loaded with about 150 rounds, giving around 15 seconds of continuous firing. Such a machine could accelerate upward to vertical speeds near 80 miles per hour. After the ammunition runs out, it would continue coasting upward, potentially reaching a height of around 200 meters before gravity pulls it back down. So, yes, With enough rifles, flight is possible. But clearly, this is not a practical jetpack. Can we do better? Consider the GAU-8 Avenger, a massive autocannon designed for aircraft. It fires 1-pound projectiles at up to 60 rounds per second and generates nearly 5 tons of recoil force. That's astonishing considering the aircraft it's mounted on produces only 8 tons of engine thrust. If you mounted 2 of these cannons on a plane and fired them forward during takeoff, the recoil alone could overpower the engines and push the aircraft backward. To put that differently, if you mounted one on a car, left it in neutral, and fired it backward from a standstill, you'd reach highway speeds in just a few seconds. As impressive as that is, an even more extreme example exists. The Soviet-designed GSH-6-30 weighs roughly half as much as the GAU-8, but fires at an even higher rate. Its thrust-to-weight ratio approaches 30. That means if you pointed it downward and fired, it wouldn't just lift off, it would accelerate upward at 30 g. 30 times the force of gravity. That's far beyond what a human body can handle. Even when mounted to aircraft, this cannon caused problems. Recoil vibrations damaged equipment. Landing lights frequently shattered. Long bursts risked heating and structural stress. Still, in theory, if you somehow built a structure strong enough to survive the forces, secured the rider properly, added aerodynamic shaping and cooling, with something like that, you wouldn't just hover. You could leap over mountains.